Hello, everyone. Welcome to lesson 32, our last lesson of Calculus 1. And what we're going to be learning about today is called the substitution method for integration, more commonly and informally known as u-sub. So on the previous few lessons, we've learned that we can use antiderivatives to help us evaluate integrals. So if we need to know the net change in a function, or if we need to know the area under the curve of a function, we can use the integral to do that. And we can compute the integral by using antiderivatives. Now, what we're going to learn today is a method of expanding our repertoire of antiderivatives, because we only are able to find the antiderivative of a few basic functions at this point. For example, the antiderivative of x raised to a power that isn't -1 is x raised to 1 higher power divided by that new power plus c. By the way, we're going to have a new notation for antiderivatives. What we're going to do is when we want to find the antiderivative of a function, we'll put it inside integral notation here. So it'll be the integrand. But the main difference is that it'll be lacking bounds. So all of these right here, all of these examples are what are known as indefinite integrals, as opposed to definite integrals, which have some sort of bound. So whenever we have an integral without a bound, we simply want to compute the general antiderivative with the plus c. All right, anyways, we know a few other antiderivatives as well. The antiderivative of cosine will be sine plus c. The antiderivative of e to the x will be itself, possibly plus a constant. But there are definitely functions out there which we don't know how to find the antiderivative of yet. And one of these, for example, is this function right here, x e to the x squared. So kind of like derivatives, antiderivatives don't work that nicely with multiplication and division, at least not as nicely as it does with addition and subtraction. So we don't really know how to deal with two different types of functions multiplied together like x and e to the x squared. Furthermore, we haven't really developed a version of the chain rule for integration. So we don't really know what to do if one function like x squared is plugged into another like e to the x. But this is where the substitution method comes in. Substitution method you could think of as the chain rule, but for integrals. It's particularly useful when we have one function plugged into another, like in this scenario. So the way we perform u-substitution is we label part of our integral u. So what I'm doing is I'm labeling this x squared, and I'm giving it a new name, u. And we typically do this to a function that's plugged into another function. All right. Now what we're going to do is we're going to turn this integral of x's into an integral of u's. And it's not quite as easy as just changing all of these to be u's right here. We need to first figure out what's going to happen to our differential. So this integral has a dx right here. And that's not just there to be annoying or to forget about. This is actually significant. This is a part of the integral. So we need to know how to change this to be a du. And unfortunately, it's not as simple as just replacing the x with a u. What we do is we come up with our substitution, then we find the derivative of our substitution. So here we have du dx is 2x. Then what we do is we bring up the differential over here. So du is 2x dx. So this is what du is equal to. Like I said earlier, it's not just going to be dx, we may have some extra stuff in there as well. Now our goal with this part of the substitution is to get rid of part of our integral here. So notice how we have an x and the dx here. These don't quite match up with this u right here because it doesn't involve an x squared. So it'd be nice if that part just went away. So what we're going to do here is we're going to divide by 2. So 1/2 du will be x dx. And that's going to be what we're substituting here. Because we have an x dx here, we could replace that with a 1/2 and then a du, which is exactly what we do in this step here. Finally, the only part of the integral that's left is e to the x squared, but now we can write that as e to the u. And there we go. We've used substitution to transform our rather complicated x integral into a very straightforward u integral. So we find the antiderivative of e to the u, which is e to the u. It doesn't matter what letter it's called here. And then We put our plus c because we've evaluated an antiderivative. And then all we need to do to finish the problem is replace everything back in terms of x, because they gave us an antiderivative of a function of x, so rightfully we should provide them with a function of x. So all we need to do is replace this u with an x squared, and voila, we have our antiderivative of x e to the x squared. It's 1/2 e to the x squared plus c. All right, so that's a pretty basic example of a u substitution. Now, I mentioned a few minutes ago that it has something to do with the chain rule. And actually, this is my second take of this video. I was recording it, and then my pen died when I got to this part. So what does this have to do with the chain rule? Well, let's suppose we wanted to do the derivative of f of u of x. Well, then by the chain rule, we would have f prime of u of x times du dx. So now what I'm going to do is I'm going to take the antiderivative of both sides of this. So the antiderivative of a derivative is the function itself, possibly with a constant. And on the other hand, I'm going to do the antiderivative here. And there we go. So this is the formula for our substitution rule, and it actually comes from the chain rule here. What we do is we substitute u into our function right here, and provided we also account for du dx, which we did in this problem here, then we should be able to integrate the resulting function of u just as easily as we would with a function of x. In fact, it'd be even easier than the original function, because usually u substitution is used to make integration simpler. So if we can replace all of our variables with u's and also fit in du dx, this process right here, then we could do the antiderivative of an easier function and get something nice out of it. So that's the formula for the substitution method. But honestly, it's not really worth it to memorize this formula or anything. U substitution is definitely something that's best learned through practice here. So let's get some practice with it. Let's say that we want to find the antiderivative of e to the t times cosine of e to the t dt. So what we're going to do here is we're going to use u substitution to do this. Now, when it comes to u substitution, it's sort of an art on picking the correct u. But in general, there are two different strategies, or there are two strategies that you should use to pick a u. So whatever you pick for your u should be in the integrand. And it's almost not worth writing this down, because this is typically how we spot our u's in the first place. For example, we had an x squared and it was in our integrand here. And here we see we have a lot of e to the t's here. So we think that might be a good choice for you. Now, the second part is something a lot of people missed. We should have du, I guess in this problem it's dt, but it could be dx as well, should also be in the integral. Because remember, we need to include that in order for this formula to work. So notice that if we take the derivative of x squared, we get 2x. And that's not exactly what we had in there, but it's only off by a constant. So we effectively had a number times x right there. So that means x squared is a particularly good substitution because itself shows up here, and then something similar to its derivative shows up here. All right, now we can apply that reasoning to this example here. So for this problem, I'm going to select u equals e to the t. This means that du will be e to the t dt. So it obviously satisfies the first part because we do see e to the t in here, but we also see u's derivative, which is also e to the t, show up in our integral. So since it satisfies both of these, that means it's a good choice for a substitution. All right, so what do we do now? Well, if I want to put du in there, I need to sacrifice an e to the t dt. This is kind of the exchange rate for turning things into u's. So I have e to the t dt, that could be traded in for 1 du. And then now I have this cosine of e to the t, but since we're writing everything in terms of u, this will end up being cosine of u. Now look at what we've done. We've turned this kind of nasty looking integral into something that's relatively easy to do. So by what we discussed earlier, the antiderivative of cosine will end up being sine of u plus c. And then the last step is to substitute back in what u is. So we end up with sine of e to the t plus c as our antiderivative of our original function here. All right. So both of the examples we looked at so far are problems that would have been essentially impossible to do without u-substitution. Now, u-substitution has more uses than that. It could also be used for problems where it would be very difficult to do without u-substitution, but not impossible. So let's suppose we wanted to find the area under the curve from 0 to 1 of 1 plus 2x to the 100th power dx. Now, in the theory, what we could do is we could FOIL this out 100 times, but that would get very nasty very fast. So we don't want to do it that way. So what are we going to do here? What we're going to do is we're going to do a u-substitution. Now, this u-substitution will be a bit different because we have bounds on our integral. This is going to be a definite integral. And thankfully, u-substitution can be used for both definite and indefinite integrals. All right, what I'm going to do, the difficult part of the integral as it's written is the fact that there are two terms here, meaning we would need to FOIL this. But if I replace this with one single term, u, then I just have u to the 100th power, which I could simply do the power rule on. So this is what motivates me to pick this as my u. And plus so I've satisfied the first criterion that I talked about earlier. It shows up in the integral, so here it is. Now let's make sure that its derivative, or at least something similar to it, also appears. So du in this case will be 2 dx. And while we don't really have a 2 here, what we can do is we can divide by 2. So we have 1/2 du is dx. It's not uncommon to do a little algebra here to kind of finagle things, so we end up having exactly what shows up in our integral here. Okay, so now I'm going to rewrite my integral. I exchange my dx for a 1/2 du, and then I have 1 plus 2x, oh, whoops, we're doing a u integral now. So we have the integral of u to the 100 du. Now, earlier we didn't have any bounds to worry about, but this time we have some bounds here. So it turns out that there are actually two different ways of evaluating this integral. So I'm going to show you the first way, which involves changing the bounds for your integral. And this is honestly the way I prefer to do most of these problems. But then afterwards, I'll show you guys an alternative way, which you may like better. A lot of people like this other way too. So the way we do this first method is we change our bounds for x into bounds for u. Because remember, these are the x values that we're finding the area between under our function. So since we're doing an integral with u now, we should change these to the matching u values. So the way we do that is we take our bottom bound, which is x equals 0. Remember, these are x values. And I plug it into here. So I have u is equal to 1 plus 2 times 0, which means that u will equal 1. So that will be my bottom bound here. Then for my upper bound, I just take whatever x was in that case and plug that into my formula. So u will be 1 plus 2 times 1, aka 3. So now rather than going from 0 to 1, my integral will instead go from 1 to 3 here. Now, this may seem like a kind of an annoying thing to do, but it'll save work in the long run here, trust me. All right, now that we've converted our integral over, now we just do the easier integral. So all we need to do the antiderivative of this is raise the power to be 101 and then divide by 101. Now multiplied by 2, that'll be 1 over 202. And we have u to the 101. And that's going to be from 1 to 3 right here. All right, and then finally, remember the way this is done is we first plug 3 in for our variable. So we have 3 to the 101 over 202. And then we subtract when we plug 1 in here. But 1 to the 101st power, as great of a power as it is, will only yield 1. So we have -1. And that will also be divided by 202. All right, so there we go. So we have 3 to the 101 minus 1 over 202, which is an astronomically large number, by the way. All right, that was the first method of doing this. Now, I also promised another method. So the other method allows us to procrastinate on changing the bounds, and it lets us keep the bounds that we had previously. But the catch is we need to put those are equal to x so we don't confuse it with this scenario and plug in these numbers directly. So for now, we can keep our bounds, and we don't have to do any work now. So we can do the antiderivative. We have u to the 101, and then we divide by 101, just like this case. And this goes from x equals 0 to x equals 1, right here. But now our procrastination has caught up with us here. Now what we need to do is, since we have x bounds, we need to change our u back into x's. So we have to rewrite this as 1 over 202 times 1 plus 2x to the 101. And now we can plug in our bounds 0 to 1. So the first method does its work right away, and then we never have to worry about changing into x's again. Notice that I don't see the letter x the entire time I did this here. Whereas in this case, I need to convert back into my x's, but I don't have to do any work back up here. So now I can plug in 1 here. 1 plus 2 times 1 is 3, and then we have that to the 101. And then we subtract, and then we plug in 0. We have 1 plus 0 is 1, and then that's to the 101. Now, see, you kind of effectively do the same work anyways. You're still kind of doing this arithmetic. You're just doing it later in the problem here. So now we ended up getting the same result. So the moral of the story is you could do this either way. I'm going to suggest doing it this way, where we change our bounds in the beginning. There will be some problems in the future where we can exploit some symmetries that come from the u-substitution to make our problem way easier. And we wouldn't be able to do that if we did this way right here. So I would recommend doing it this way, but it's not wrong to do it this way right here. All right, so that's a definite integral. All right, let's try another problem. This one will be a little bit trickier to identify what u has to be. And this is why I said it's kind of an art. Sometimes it's very difficult to identify what u is. And in fact, for some problems, there's actually more than one u that you could pick, and both wind up being correct. Anyways, let's take a look at this problem. This is another definite integral. This one's going from -1 to 1, and then we have x over 1 plus x to the 4th dx. All right, now this is pretty clearly something we need to use u-substitution on because we don't have any version of the quotient rule for antiderivatives. So hopefully we can use u-substitution here. Now, one thing that might be rather tempting is to use u equals x to the 4th, or maybe even 1 plus x to the 4th. So if we try doing that, let's try with the 1. Then we have du is 4x cubed dx. But the problem with this is that we don't have any x cubes in our integral. Presumably this will turn into a u, but we just have an x up here. We don't have an x cubed. The 4 isn't a big deal because we just divide by 4 if we need to, but we can't just multiply both sides of this by x squared, at least not very easily. So this is going to leave us in a lurch right here. So I don't think this is a very good substitution. And going back to the criterion we established earlier, this does satisfy criterion 1 where it does appear in the integral, but nothing like its derivative shows up. Okay, well, let's think about this. What kind of functions have a derivative of x? Well, we saw in an earlier problem that x squared has a derivative of 2x, and then maybe we could divide by that 2 if we need to. So let's try that substitution. Now, at first, this seems like it violates the first kind of obvious rule that it doesn't appear in the integral. But upon closer inspection, we do see that technically this here is x squared squared. So this really does appear in our integral, just not right away. So it does satisfy condition 1. And then if we find the derivative and divide by 2, it also satisfies condition 2. So both the u sub itself and its derivative shows up in our integral. So this is what we're going to do. This is the u sub that's going to end up working out for us here. All right, so now we found a u sub that works, so let's go ahead and substitute this in. So we have our integral. Our x dx right here will turn into 1/2 du. Then in our denominator, what we end up getting is 1 plus u, so this is a u right here, but then that itself is squared. So I have 1 plus u squared. All right, and now I'm going to show you why way 1 ends up being better than way 2, right? I guess I should call these methods. It kind of sounds weird to say ways. This is why method 1, substituting earlier, tends to be better than method 2, substituting later. Let's go ahead and do method 1 here. So what we do is we change our old bounds into some new u bounds. So for example, I take -1, I plug that into here, and I square it, and I get 1. So that's going to be my new lower bound. Then I take my upper bound, and I plug it into the formula. I have 1 squared, which is also 1. So then I plug that into the formula. And this is what I was hinting at earlier. Sometimes if we use method 1, we end up with this scenario here, where it actually doesn't matter what our integrand is. This is an integral from 1 to 1, or more generally a number to itself. This is automatically going to equal 0 without us having to think about what the antiderivative of that is at all. On the other hand, if we use method 2 here, we would have this as our integral. And while this isn't an impossible integral, this actually ends up being arctangent of u. So this will be 1/2 arctan of u from x is -1 to x equals 1. This step we skipped entirely, and we immediately got our answer over here. Now let's see how this ends up being 0 the longer way. I substitute back in my u. I put in back in x squared for that. And now I can omit the x equals because now x is our variable. And then we end up with 1/2 arctan of 1. And then we subtract and do the same with the lower bound. But that will also be 1/2 of arctan of 1, because -1 squared will be 1. And those cancel to yield 0. So this is why I generally prefer method 1, because method 2, you won't be able to see shortcuts like this, where you have something nice happening. So this is why I prefer method 1. But you're always welcome to do method 2, though. Some people are more comfortable with that. All right, now this integral ended up being 0. So what's actually happening with this? It turns out that the signed area on the positive end of this canceled out exactly with the signed area on the negative end of this. Now, this isn't just a special feature of this function in particular. This is actually a feature of functions which are known as odd functions. So there's a special property involving odd functions and integrals. All right, so let's review what an odd function is. So what is an odd function? An odd function is where if we have f of -x, then the function spits out the negative sign, and that's the same as negative f of x. So that's what an odd function is. Now, odd functions have the property that if we integrate them on a symmetric interval, so from negative a number to the positive version of that number, we're going to get 0, no matter what the function itself is. And we can see that this is an odd function here. So let's say f of x is x over 1 plus x to the 4th. because f of negative x will be negative x over 1 plus negative x to the fourth. But a negative to the fourth will just be a positive, and I'm going to move this negative to the front. But then this is none other than negative f of x. So this is why that function was an odd function. And because it's an odd function, integrated along a symmetric interval, we're going to end up getting 0 for that. Now, you may remember, in addition to odd functions, we also have even functions. It turns out that there's a nice trick for that as well, but it's not the same as the one for odd functions. So let's check out what happens with even functions. And in case you've forgotten what an even function is, if we have f of negative x, rather than spitting out the negative sign, I like to imagine that it swallows the negative sign. So it can just disappear like this. So if we have an even function, then what happens if we integrate it over a symmetric interval is that we can, rather than doing this, we can instead replace the integral with 2 times the integral over half of the integral, half of the interval. Interval and integral kind of sound similar. So if we integrate an even function over a symmetric interval, then that's equal to twice only going over half the interval. All right, so to demonstrate this, let's take a look at the integral from -1 to 1 of x to the fourth plus x squared plus 1 dx. Now, when it comes to polynomials, if all of your powers of x are even, and that includes 0, then your function is going to be an even function. So let's go ahead and use this property right here to help us solve the integral. So this is going to be equal to 2 times the integral from 0 to 1 of the same thing. All right, so now we have 2x to the fifth over 5 plus x cubed over 3 plus x. That goes from 0 to 1. All right, so I go ahead and plug 1 in for all of these. So I have 1/5 plus 1/3 plus 1. All right, let's combine some fractions here. This is going to be 46 over 15, if I'm not mistaken. There we go. So that's going to be our result for this. Now, if we would have just done the integral normally, you might wonder why this actually saved us a bit of time or why this was helpful. If we would have done this normally, then we would have had more arithmetic to deal with. Because what would have happened is we would have evaluated this from -1 to 1. We would have plugged in 1 for all of these. But then we also would have had to subtract and plug in -1 for all of these as well. So we would have had a fair bit more calculation in this part right here. Although what's going to happen is that this negative sign is going to negate all of these negatives. And what we're going to end up with is just another copy of this. Hence why we have 2 of this right here. There's kind of an intuitive reason as to why this is going to work. But anyways, if you ever have an even function, you want your bottom bound to be 0, because having a bottom bound of 0 is nice, you can go ahead and use this trick here. I honestly think the odd function trick is really nice because you could just replace the whole integral with 0. So if you ever spot an odd function over a symmetric interval, don't bother actually doing the work for it. Simply remember that it's going to be 0. All right, that's it for today's lesson. I guess that's it for the whole course. So if you decide to continue into Calculus 2, we're going to learn a lot more techniques for integration, because it turns out that there are still going to be functions that we don't know how to integrate, even with u-substitution. Like, for example, while we were able to integrate x e to the x squared earlier, we still don't know any techniques that would allow us to find the antiderivative of something like x e to the x, even though that would be a really easy function to do a derivative of. So if you join us for Calculus 2, we'll learn more about these antiderivatives, among other topics as well. All right, so I will see you guys in those videos if those videos come out. So have a good one.